we are looking at a vertex in this graph whose degree is at least 2 now, and we are branching on this vertex. We are saying either u goes to the solution or u does not go to the solution. If u does not go to the solution, that n of u has to go to the solution. In this case, we are saying do this, create this instance, and in this case we are saying create this instance. And we know that this value is at most k minus 2 now, right, because n of u is at least 2, right, and this value is k minus 1, right. So now when I further branch for this instance, I get a branching tree. Again, it will not be a complete binary tree, because again for this also when I branch, I will get an instance where it is some g, and this will be k minus 2, and here I will get some k minus 3. Here I will get k minus 3, and here I will get k minus 4, right, this sort of a thing. So the point is yeah. So I will not get a complete binary tree on k vertices at least here. So it looks like the number, it does not look like, definitely the number of nodes in this branching tree, in such a branching tree will be less than 2 par k, right. So we have to, but we have to see how much it is to get a perfect bound. That is one thing. So we will do that, we will compute the total number of nodes in this tree, but before that, is it okay like every time I find a vertex of degree at least 2 and branch on it, right? What happens if I am unable to find a vertex of degree at least 2? Yes, so as he says, if I am unable to find a vertex of degree at least 2, how will that graph look like which has no vertex of degree at least 2? It will just have edges, right? So like for example, I keep on doing this branching, and suppose at one point I am at an instance g prime k prime, and g prime has no vertex of degree at least 2. That means every vertex has degree 1, and we know that g prime is nothing but a collection of isolated edges. Now in this graph, instead of branching, I can just solve the problem in polynomial time, right? Again, why are we branching? See, eventually for every instance I want to solve that instance. I want to say if it's a yes instance or a no instance, because to solve that I'm solving that recursively. But if at any point I find an instance that is easy to solve, why would you want to further branch on it, right? Your aim is anyway to solve it. So if at any point you find an instance that you think is easy to solve, just solve it and don't branch on it, right? So we can always branch on degree 2 vertices, and if the graph has no vertices of degree at least 2, and if a graph has no vertex of degree at least 2, we know that such graphs can be solved very easily. So you don't branch further. So these will be the leaves of your branching tree, like you will not branch further on these trees. So again, you can always do that. You can always do this kind of a branching. Get a vertex of degree at least 2, branch. Again, the total running time of this algorithm will be the total number of vertices in this branching tree into the time taken at each branching node. Note that at each internal node, again, what are you doing? You are checking if it has a vertex of degree at least 2. Can you do it in polynomial time? Just go and check the degree of every vertex, right? And if you find one such, branch on it. And look at the leaf nodes. How much time? See, in the previous case, we were spending constant time on leaf nodes. Okay, not really constant. At leaf nodes, we were checking if the graph is an independent set in the previous case. Here we have to do something different. Here we have to we know the leaf node, the graph will on these kind of leaf nodes. These kind as in where g prime has no vertex of degree at least 2. On these kind of leaf nodes, we know that this graph has to be isolated edges. And what do we need to check now? There should not be more than k prime of these edges, right? Because from each edge I have to pick some. So basically in this graph I have to check if this graph has a vertex cover of size at most k prime. This is equivalent to checking if the number of edges in this graph, because it's only a collection of disjoint edges, the number of edges in this graph is at most k prime. So you can do this in polynomial time and solve this instance, such instances of leaf. Again, this is a polynomial time procedure, some polynomial. So leaves are either of this kind, or again the leaves could be of this kind. Maybe you're always able to find vertices of degree at least 2, and then you stop when k goes to 0, k becomes 0. And you know that you can solve, like, these leaves also you can handle in polynomial times. You can solve these kind of leaf instances also in polynomial time. So at every node we are not spending more than polynomial time. We are doing different kind of polynomial time procedures for different kind of nodes, but whatever we are doing, it's a polynomial time thing, right? So again, the running time of this branching algorithm is also equal to number of nodes in this branching tree into time taken at each node, which is polynomial, and this is some polynomial. So again, it boils down to finding how many nodes are there in this branching tree, right? And again, as I said, to compute we know that the number of nodes in a branching tree is basically equal to 2 times number of leaves minus 1, because it's number of leaves plus number of internal nodes, and because each internal node in a branching tree has at least 2 children, so the number of such internal nodes is not more than the number of leaves minus 1. So it's number of leaves plus number of leaves minus 1, which is 2 times number of leaves minus 1. This is because of this, right? So basically to compute the running time of the branching algorithm, it's enough, like all we need to do is we need to bound the number of leaves in this branching tree, right? So, I mean, how do you think, how can you bound the number of leaves in this branching tree? Again, try to write some sort of a recurrence to do that. We had an instance g comma k, and to solve, like, yeah, and then we are making instances which are g this and g minus n of u, comma, and this is at most k minus 2. Okay, if you want to write a recurrence, then how should it look like? So we are interested in bounding the number of leaves, okay, in this branching tree. So let us say that, to bound the number of leaves in this branching tree, in order to write a recurrence, we can write a recurrence saying that, okay, the number of leaves in this branching tree is equal to the number of leaves in this branching tree plus the number of leaves in this branching tree, right? If I have to solve it using a recurrence, how many leaves are there in this whole branching tree? It's equal to the number of leaves in the branching tree. Like, look at the branching tree, which is rooted at this instance, and a branching tree rooted at this instance. If I'm able to compute the number of leaves here and the number of leaves here, then I'll just add both these leaves up to get the number of leaves in the total branching tree, right? Right? So now can you think of any recurrence? Okay, one thing, the number of leaves in any branching tree, what do they depend on? Like, do they depend on n or the number of vertices in the graph? Will they depend on the number of vertices in the graph? Levels, and levels, what do the levels correspond to here? Like k, right? It depend on k. So the number of leaves in the branching tree, they don't depend on the number of vertices here, right? They depend on k, right? So try to write a recurrence in terms of k. So let's say, exactly. In fact, let me just write t so that people don't think that we are doing anything different here. So let's say tk denotes the number of leaves in a branching tree, which is branching tree corresponding to, for example, the branching tree, let me say rooted at gk. So the branching tree rooted at gk is the whole thing, okay? gk, or in fact branching tree which is rooted at an instance where the value, the parameter is k, right? Because the depth will depend on k. And so tk minus 1 corresponds to a branching tree which is rooted at an instance where the parameter or the k value is k minus 1. tk minus 2 refers to the branching tree rooted at instances where the parameter value is k minus 2. I don't care what graph there is. So for example, if at this node there was some different graph but k was same, then the number of leaves that I would get there, like it doesn't matter if what graph here is, right? The number of leaves are only dependent on what k values I'm getting here. So are you convinced that the total number of leaves in this branching tree would be like, for that we can write this recurrence, right? So so when we're writing a recurrence, we have to write a base case also. So what is T1? T1 corresponds to the case when, or let us say T0. T0 corresponds to a case when you have a graph with 0. How many leaves are there in such a tree? So you have this graph G prime and you are 0. So there is no tree below it, right? So the only tree here is only the single vertex. So T0 will correspond to 1. So there is only one leaf that corresponds to such instances, because that tree is nothing but that single vertex, right? So basically you have to solve this set of recurrences, right? What should this solve to? In fact, if T0 is confusing to you, you can actually write T1 is equal to 1. Why? Because what is T1? T1 will be corresponding to instances which are of the form T prime and 1, right? I mean, all I'm saying is you don't go till k becomes 0, you just go till k becomes 1. Even that instance you can solve easily, right? Because you just have to check if there is one vertex whose deletion makes the graph an independent set. So if this is, so you can write, so maybe your base case would be when k becomes 1, so T1 is 1. Okay. So you have already seen such a recurrence, right? I've just only, what does this recurrence solve to? It's the same recurrence, right, in a different variable. But now it will be 1.618 to the power k and not n, right? So basically we have bounded the number of leaves in the branching tree by this. So the total number of nodes get bounded by twice into 1.618 per k minus 1. This is, yeah, and hence the total running time becomes this number into time taken at each node, which is some polynomial. Of course, as in homework, you can try to see what is this polynomial. So we are doing some simple things, right? Checking if the graph is an independent set and so on. You can just, it will not be, most of these procedures are linear time procedures. So it will actually be into n. Okay, so, but I'll leave that as an exercise. And so basically this is nothing but all these constants can go into this term. And this is actually a 1.618 per k into poly n algorithm. Again, so the only thing in branching algorithms basically is like a branching, and then seeing when we stop, we need to see, like branch on some things, and then when you're not able to branch, you should be able to solve those instances in polynomial time, and you should be able to bound the total number of nodes in the branching tree to get to, fine. So that's it for vertex cover. I mean, you can do something more. You can improve this running time to 1.4656 per k. And how you can do that basically is, you can design a reduction rule which gives you this sort of a recurrence. So instead of k minus 2, if you can say that, okay, there'll always be a drop of at least 3, then you can get this kind of a recurrence there, right? How can you get this kind of a recurrence? For example, if you start with a vertex whose min degree is at least 3, you'll get this recurrence, right? And this recurrence basically solves to this value. So you'll get this value. But now you have to see that, okay, if you don't find a vertex of min degree, if you don't find a vertex of degree at least 3, then your graph, every vertex in your graph has degree at most 2. Again, it's very simple to check, to compute a vertex cover in graphs where every vertex has degree at most 2. How will those graphs look like? There will nothing be paths and cycles, and those graphs you can compute the vertex cover easily. Right? So you can actually get this. So I'll leave this as an exercise to prove that this recurrence will solve to this. If there are doubts, we'll discuss this in the tute. But so you can write this recurrence and actually get this kind of a running time. So we stop with vertex cover here, and we'll do another example just to see a different flavor sort of a thing. We want to design an Fpt algorithm for a different problem, again using branching. And the different problem is a dominating set problem. Have you seen the dominating set problem? Have you? Okay, I'll still define it. So in the dominating set problem, it takes as input a graph G and an integer K, and it outputs yes if there exists a set of vertices, say S, of size at most K, such that for every vertex in the graph, either this vertex belongs to S or some neighbor of it belongs to S. And outputs no if there is no such set. Again, so what is a dominating set? It's a collection of vertices such that look at any vertex, either that is in the set, or if it is not in this set, one of its neighbors is in the set. Right? So if S is a dominating set, look at any vertex that is not in S. One of its neighbors has to be in S. Right? Or in other words, you can actually think, you know this concept of a closed neighborhood of a set, right? Like closed neighborhood of a set is nothing but the union of the neighborhoods of all the vertices in S, including S. So if S is a dominating set, what is the closed neighborhood of S? Look at any vertex in the graph that has to be a neighbor of some vertex of S. Sorry? Okay, it is, but then I think I'm not able to convey the definition of n of S. So n of S, this is the closed neighborhood. Okay, so okay, let me write n of S. You are right, but I think you don't get this definition right. So n of S is equal to S union neighborhood of all vertices in S. This is n of S. So n of S has S in itself. So now can you tell me, if S is a dominating set, then what will be this n of S? All the vertices. Because any vertex, it's either here in S or in okay, I did something fancy here. Any vertex, it's either here in S or it's in some set here, right? Fine. So suppose we wanted to solve dominating set, again parameterized by K, so we wanted to get some, let us say some C par K, where C is some constant, 10 par K, 100 par K, any 10 par K into polynomial in N, kind of an algorithm for dominating set. Okay. Then okay, can you think of any branching procedure that you can do for dominating set? For vertex cover, for example, what did we do? We found a vertex and its neighbors. We knew that if this vertex is not going, then all of its neighbors have to go, and we branched. For dominating set, can you find some structure over which you can branch? I mean, so what is a branching algorithm doing? See, it's trying to identify a structure and say that, okay, any solution cannot pick nothing from this structure. For example, for vertex cover, you had a vertex and its neighbors. You knew that there is no solution that doesn't pick V and doesn't pick all its neighbors. And using that information, it branched, either this or that. So for dominating set, suppose you pick a vertex. So either the solution pick this vertex. If it is not picking this vertex, then what can you say? One of the neighbors. So maybe we can branch on all the neighbors, at least as of now. It will not give you a good algorithm, but this is the starting point of a branching algorithm. So we know that, look at any V, either U belongs to the solution, or let's say if the neighborhood of U is V1 to some VD, then either U belongs to the solution. If U does not belong, then either V1 belongs to the solution. If this does not belong, then either V2 belongs to the solution, and so on, or either VD belongs to the solution, right? It could, see, there could be some subset of the neighbors belonging. all we are saying is at least one of them will belong. Okay, this is important. What we'll do is, if U belongs, we'll come to it, because anyway what we are doing is, there is this. See, if any subset belongs, when I say V1 belongs, I'm not going to delete all of V2 and VD and all those things. If they belonged, I'll look at this instance where I know that V1 belongs, I'll look at that instance and do something. So if they belong, they'll be solved when I'll be solving that instance recursively. But anyway, there are a couple of, so yeah, there is a slight catch there. I mean, I'll come to it. Okay, as of now, it's like, we know that if either U belongs or one of its neighbors belongs, right? So what is one problem that you see? It's like the number of neighbors of any vertex could be very large. First of all, what kind of a branching algorithm it will give? You'll start with a graph G comma K, and you'll branch into how many branches? Yeah, D plus 1 branches, right? And of course, and what the depth of this tree would be, again, at each point we'll reduce K by 1, because we are deciding to put a vertex in the solution, right? So the depth of this naively will be K. Okay, note that in all these algorithms, we are just now henceforth, I mean, all as in, I think I'll have time only to do this. In these algorithms, we're just trying to design some Fpt algorithm. We are not trying to optimize it. For example, for vertex cover, we designed a 2-par K, and then we saw if we can do something better, and then something better. We are not trying to do it. So any naive algorithm that gives us an Fpt algorithm will work. Okay. So naively, there are D plus 1 branches, and we know that the depth of this branching tree will not be more than K, because at every point we are decreasing K. Okay. So roughly, so let's say this looks like a D plus 1 array tree. Right? It's a complete tree where every vertex has D plus 1 children. So how many nodes are there in this tree? Roughly? Yeah, something like D plus 1 par K plus 1, something like that. Or let's say the number of leaves is D plus 1 par K. So the number of nodes is again some function of this. So see, if D was small, right? Like if D was small, then small as in if it was some constant, then this is an Fpt algorithm. But for example, if there is a vertex whose degree is say n by 2, right? Then this D will be n by 2. This will only give you a n by 2 plus 1 par K algorithm. This is not an Fpt algorithm, because in an Fpt algorithm, this thing should be a function of K alone. It cannot be a function of n. Right? What is an Fpt algorithm? We're trying to design an algorithm which is f of K into poly in n. So this n power this is some absolute constant. This can't depend on K. And this running time, this is n power K sort of a running time. And the good thing is, or the bad thing is, for dominating set, we cannot have an algorithm of this form. So it's not like maybe there is a different algorithm that, or like a natural thing would be, maybe we can try to find a vertex of small degree and branch on it. And then if we are not able to find a vertex of small degree, then maybe we can solve those instances in polynomial time, but that can't happen, because dominating set cannot have an algorithm for this form. Again, as I said, there is a theory for hardness behind these kind of problems. Again, we'll see probably in the last lecture for dominating set, we'll see why it can't have such an algorithm. Of course, assuming certain things, assuming certain conjectures which people believe to be true. Okay, so we can't have such an algorithm. So, but we know that, okay, if suppose to begin with, I started with a graph whose max degree, so this denotes the max degree of the graph. Max degree is at most D. Then can we do something, and D is some constant. Then there is a hope, right? So we know that in those cases, this D will not be some function of n. D is some constant. So what I'm trying to say is, let's try, for dominating set, we know we can't design an Fpt algorithm. Let's try to design an Fpt algorithm for dominating set on graphs of bounded degree. So as input, we are given a graph, and we know that every vertex in this graph has degree at most D. And D is like, pick your favorite number, it's some constant. Degree at most 5, degree at most 6, just fix it. Okay. So in those cases, now there is a hope to do a branching algorithm, because now when I branch, I'll branch into D plus 1 many branches. D is a constant. So the number of nodes in this branching tree would be D plus 1 par K, and D is a constant. So it is some constant par K, which is this kind of a function, right? Right. So yes, so if we are able to branch like this, then we know that the number of nodes is some D plus 1 par K, and hopefully we have we have to see that at each node we spend some polynomial time, and that will give you a d plus 1 par k into polynomial in n algorithm for dominating set, right? But let's see, but there is a like slight catch here. So let's carefully see what do we do when we branch. In GK we take a vertex in this graph and we branch. Let n of u be equal to v1 to vd, d is a constant. So what instance, like suppose I decide to pick u in the solution. So what is the instance that I should be solving here? G minus u k minus 1. Is everyone convinced that we should be solving this instance? So you are saying delete, so this represents closed neighborhood of u, so it means u is also included in this set, this if I use the square brackets, okay. So you are saying this comma, okay. Anyone else with anything? Okay, I tell you that both these things are wrong. Can you think of why? See, when I say u belongs to the solution, see for vertex cover, if something belonged to the solution, we deleted it. Why was it correct there? Yeah, because all the edges incident on it were covered, and if G had a vertex cover of size k, then G minus 1 will have a vertex cover of size k minus 1. In dominating set, suppose I have a graph which has a dominating set of size k. Is it true that if I look at a subgraph of it, like for example vertex cover we said, right, if you have a graph, if this has a vertex cover of size k, then every subgraph of it will have a vertex cover of size at most k, because look at the same vertex cover, that is a vertex cover for any subgraph, right? For dominating set, is it true, if I have a dominating set in a graph of size k, then is it true that every subgraph of it will have a dominating set of size y? Give me an example where it doesn't hold. So intuitively, why should that not be true? Mimiko? C4, okay. Oh, take okay, another vertex. Cool, very good. So this is the graph. What is the minimum size of a dominating set here? 1. So this graph, so if suppose I had an instance this will always be a yes instance. This graph has a dominating set of size 1, right? Now I deleted this vertex. I look at G minus V. Will G minus V have a dominating set? So basically when you delete V, you will say, okay, put k equal to k minus 1. So this will become 0 because you've already picked u in the solution. No, okay, forget it. You don't have to do that also. So look at G minus V. What is the size of a dominating set in G minus V? G minus V is a cycle. It is, forget, does it even have a dominating set of size 1? No matter what vertex you pick, you will not be able to cover some edges. So its dominating set is at least 2, right? So this is what makes dominating set harder than vertex cover, okay? In like harder or at least different, let's say different than vertex cover, that there it's not like, because dominating set becomes a global property. Vertex cover in some sense is a local property, in the sense that a vertex V is helpful, okay, a vertex V can cover all its neighbors, and okay, or in other words, a vertex V will cover all the edges incident to it alone. So when I delete V and I delete all the edges and I look at the remaining graph, in the remaining graph whatever edges are remaining, anyway the vertex that I have deleted, it would not have helped me to cover those edges. So whatever remains in the resulting graph, it can be covered only using the vertices that are remaining. The vertex that I delete can't help me to cover that, because the vertex that I deleted only helped me to delete edges that were incident on it, and I have anyway removed them. Here a vertex is helping to cover vertices, right? So when I delete that, when I delete that, and when I look at the resulting graph, there are vertices which need to be dominated, but the vertex that I have deleted has already dominated many of them. So it's it's like when I delete it, I lose a lot of information. Let me just put it this way. When I delete a vertex, it was dominating a lot of other vertices, and when I just delete it from the graph, I've forgotten the fact that it has already dominated some vertices, and I don't need to dominate them again, because if you look at the remaining graph, you'll again try to dominate all the vertices in this resulting graph. So what are you trying to do here? You deleted V and you're trying to find a dominating set for this graph. In other words, you're trying to find a set which picks such that for any vertex, it picks that vertex or it picks something in the neighborhood. But note that when I've decided to pick V, I know I've dominated all these things. So in the resulting graph, why am I trying to dominate all these things again? So let's take another example. Suppose the graph was this cycle, this vertex, and maybe it was one more vertex like this. Suppose I decide to pick V. So you delete, so as of now you delete V, and so now the graph looks like this. When I delete V, I know I've already dominated these 4 vertices, because these 4 vertices were adjacent to V. So in this graph, all I need to do now is try to find a dominating set that dominates this vertex, right? In this graph, I don't want to dominate all the vertices again. I just want to dominate some vertices which V has not already dominated. Right? So this gives us some idea. So basically what we can try to do is, if we decide to put V in the solution, okay, when you decide to put V in the solution, just mark all its neighbors, okay. And what does this marking say? This marking says that, see, look at all the marked vertices, they have already been dominated. So now, like, we'll be solving a slightly different problem. It's not really a dominating set. So we want to find a set of vertices which dominate the unmarked vertices. Like, we don't want, like, it might dominate some marked vertices, but we don't want it to dominate the marked vertices. Like, we know that these vertices have already been dominated from, if I'm picking U, then all its neighbors are already dominated. So in the resulting graph, you're trying to find a dominating set that dominates the other things. And as you said, so clearly this will not hold. If I just delete U from the graph and I look for a vertex cover, dominating set of size k minus 1, this will not hold. Because I've not remembered the fact that there were some vertices which U has already dominated and I don't need to dominate it again, basically because of this example. And now why is this wrong? Exactly. So if I delete the neighbors, we know that the neighbors have been dominated, but they might, like in this, for example, in this graph, the one with this extra vertex, if I delete the neighbors of U, okay, not in this graph, but in general graph, so if I delete the neighbors of a vertex set, of course they were dominated, but these vertices could help to dominate some other vertices in the graph. For example, let's say it was this graph. So there were a lot of pendant vertices associated with, okay. So the graph is, suppose the graph was this, and there is this vertex which has a lot of these vertices. Now we deleted V, and of course we have dominated, when we delete V, we have dominated all its neighbors were this. Now if I delete them, I have these vertices remaining to dominate, right? But the best way to dominate these would be to pick this vertex, right? If I delete them, then I will pay a lot to dominate these vertices, right? So even this you can't do, because the neighborhood of U is dominated, but you might want to pick them to dominate some other vertices, right? So these things we can't do. So rather, as we said, what we can do is, instead of deleting vertices, let us try to mark vertices, okay? So what does marking represent? Let us at any point of time mark vertices, and the marked vertices will represent that they have already been dominated. So for example, when I pick U, I'll mark U and the neighbors of U, because when I decide to pick U in this solution, I know U is dominated and all its neighbors are dominated, okay? And now at any point of time, we are trying to find a set of vertices that dominates the unmarked vertices, right? So basically we try to solve a slightly more general problem. So let's call it Let me just give it a name. Marked dominating set problem. So there, suppose you are given as input a graph G and a set of vertices Vg. Okay, I should write it on the next page. Okay, can I take 2 minutes? Okay, so let me just quickly do it. There's already time. Okay, so in the marked dominating set, suppose I'm also given a set of vertices, okay, which and output is yes or no, and it yes if there exists a set of size at most k such that it dominates G minus x. So basically, you look at the neighborhood of S. In the neighborhood of S, all the vertices of Vg minus x should be there. It could dominate some vertices of x or not, but it should definitely dominate everything which is outside x. So this x represents those vertices that we would have marked so far, which we don't want to dominate, like which we do not really want a solution to dominate these vertices. We do not want it to necessarily dominate these vertices. So now when we do basically, okay, note that to solve the dominating set problem, you can start with an instance where x is phi. So if x is phi, you are looking for a set that dominates everything. So basically it's a recursive instance. So this is a general instance. You will start when x is equal to phi. You take a vertex, decide if this goes to the solution or one of its neighbors goes. So when you decide to put a vertex in the solution, what you do is you create an instance where it's g comma k minus 1 because you've decided to put it in the solution, and you update x. In x you put all neighbors of u. So in this graph you are trying to find a dominating set that dominates all the remaining things. To start with, this x was phi. So when you decided to put u in the solution, in this instance you are trying to, so this is the instance, so x is this in this instance. In this instance you are trying to find a dominating set that dominates all the vertices that were not covered by u, because the vertices of x were already covered by u. So you only want to dominate whatever remains. And if there was a dominating set in G that was covering everything, then there is a dominating set in one of these branches, because that dominating set would be picking one of these things, and if you pick u, you would have already covered n of u, and then the remaining things will be dominated by that solution minus u.